This content is produced by Darknet Breaker, a cybersecurity and dark web education brand. All videos, posts, and content are strictly for educational and awareness purposes only. We do not promote, support, or encourage any illegal activity. Our mission is to expose digital threats, protect online users, and educate the public about cybersecurity risks in the modern world. Stay ethical. Stay protected.
State-sponsored intelligence agencies are currently ingesting encrypted darknet traffic in bulk. They're following a strategy called Harvest Now Decrypt Later, collecting vast archives of secure communication and storing them in massive data centers, waiting for the hardware to catch up. Tor's current encryption provides effective protection against today's supercomputers. However, adversaries are treating these inactive archives as long-term assets, betting that the underlying mathematics will eventually become vulnerable. This protection currently relies on the Tor handshake. During circuit creation, the client and relay negotiate shared secrets using elliptic curve Diffie-Hellman, specifically utilizing a mathematical structure known as curve 25519. Reversing the discrete logarithm problem for this specific curve is computationally infeasible for classical processors. At this moment, this geometry effectively isolates darknet traffic from surveillance. This anonymity remains effective only as long as the computational cost of reversing the math stays high. If the hardware environment changes, the protection afforded to these stored archives vanishes. The development of a functioning quantum computer capable of running Shor's algorithm changes that cost calculation. Shor's algorithm bypasses the linear trial and error approach of classical machines. By exploiting the properties of quantum superposition, it can determine the private components of an elliptic curve in hours. This capability applies retroactively. A quantum machine will decipher the traffic harvested today, exposing identities and communications that were intended to remain private for decades. Tor engineers must deploy quantum-resistant mathematics now. Protecting the data being transmitted this second requires the network to anticipate a hardware environment that does not yet exist. To counter this, the National Institute of Standards and Technology, or NIST, has standardized a new category of math, post-quantum cryptography. Algorithms like ML-Chem rely on the geometry of high-dimensional lattices, a problem set that remains difficult even for quantum processors. Integrating this new math is complicated by Tor's physical architecture. To prevent traffic analysis, the network transmits data in fixed 514-byte cells. Each contains a 5-byte header and a 509-byte payload. Standard elliptic curve keys fit comfortably in that space, but an ML-Chem public key requires over 1,000 bytes. It is physically impossible to fit a post-quantum key into a single Tor cell. Attempting to transmit these massive keys through the existing, rigid architecture causes the circuit to fail. The legacy pipeline is too narrow for the data volume required by quantum-secure math. Adopting quantum security is an engineering bottleneck. The move to stronger math is restricted by the very packet size rules that make Tor anonymous in the first place. The Tor project is currently developing an engineering response through proposals 269 and 340. The solution is fragmentation. The oversized ML-Chem key is divided into chunks that fit into the 509-byte payloads of multiple cells. Cell packing fills the remaining space with other data to maintain efficiency. The sequence travels across the circuit and reassembles at the final node. This approach increases the risk of handshake failure. If the network drops just one cell in this fragmented sequence, the entire cryptographic exchange is invalidated, forcing the client to restart the connection. Managing this size bottleneck changes the fundamental behavior of data on the network. To maintain anonymity, Tor's internal mechanics must undergo a significant architectural mutation. Even with the successful integration of ML-Chem, cryptographers remain cautious. Lattice-based math is relatively new. There is a possibility that a researcher could find a classical shortcut to break ML-Chem using standard hardware, effectively bypassing the quantum protection before it's even needed. To avoid this, developers use a transitional hybrid handshake, layering curve 25519 and the new ML-Chem algorithm. Here, an attacker must break both problems simultaneously. Classical attacks bounce off the elliptic curve, while quantum machines are stopped by the lattice. Cryptographic security is built on the assumption that any single algorithm might have a flaw. Layering them ensures that a weakness in one does not compromise the entire system. These changes are being integrated through a parallel implementation of the Tor protocol written in Rust, called ARTI. This transition is designed to be seamless. The network's internal mechanics will change without any visible impact on the browsing experience. As hardware becomes more capable, the mathematical barriers protecting anonymity must be adjusted to maintain the same level of difficulty. If the architecture doesn't adapt to accommodate these larger, more complex barriers, the original promise of unlinkability becomes impossible to keep. To stay anonymous in a rapidly advancing quantum world, the underlying protocol must evolve to meet the challenge. Stay secure.